Namaste, and once again welcome back to another session of online mathematics class. Last class we have started the topic maxima and minima, and we have discussed some problems in exercise 6.5. Today we are going to discuss two important theorems, namely the first derivative test and the second derivative test. And after that we will discuss the remaining problems in exercise 6.5. Let me start. First of all, we shall discuss the first derivative test. First derivative test. Let f be a function defined on an open interval I. F be a function defined on an open interval I, and let f be continuous at a critical point C. So by critical point we mean either f dash of C is equal to 0 or f is not differentiable at x equal to C. Then we can say C is a critical point. Okay, a point C in the domain of the function f is said to be a critical point if either f dash of C is equal to 0 or f is not differentiable at C. Okay, so here f be a function defined on an open interval I, and let f be continuous at a critical point C in the interval I. Then first point is, if f dash of x changes sign from positive to negative, f dash of x changes sign from positive to negative as x increases through C. Okay, f dash of x changes sign from positive to negative. That means if f dash of x is greater than 0 at every point sufficiently close to and to the left of C, and f dash of x is less than 0 at every point sufficiently close to and to the right of C. Okay, then we can say C is a point of local maxima. C is a point of local maxima. Okay, now look at the second point. If f dash of x changes sign from negative to positive as x increases through C, that is f dash of x is less than 0 at every point sufficiently close to and to the left of C. That means if we put the values sufficiently close to and to the left of C, the value of f dash of x, the sign of f dash of x is what? Negative, and if you put the values to the right of C or sufficiently close to and to the right of C, the value of f dash of x is, the sign of f dash of x is positive. So the change is from negative to positive as x increases through C. Then we can say C is a point of what? Local minima. C is a point of local minima. Okay. And the third one is, if f dash of x does not change sign, there is no sign change, then what we can say, C is neither a point of local maxima nor a point of local minima. In fact, such a point is called what? Point of inflection. Point of inflection. Okay, I repeat. Let f be a function defined on an open interval I. Let f be continuous at a critical point C in I. Then first one, if f dash of x changes sign from positive to negative as x increases through C, that is if f dash of x is greater than 0 at every point sufficiently close to and to the left of C, and f dash of x is less than 0 at every point sufficiently close to and to the right of C, then C is called a point of, C is a point of what? Local maxima. And the second point is, if f dash of x changes sign from negative to positive as x increases through C, that is if f dash of x is less than 0 at every point sufficiently close to and to the left of C, and f dash of x is greater than 0 at every point sufficiently close to and to the right of C, then C is a point of local minima. Okay. The change of sign is from positive to negative. Then we can say C is a point of local maxima. And the sign change is from negative to positive. Then we can say C is a point of local minima. In some situation, f dash of x does not change the sign as x increases through C. Then C is neither a point of local maxima nor a point of local minima. In fact, such a point is called what? Point of inflection. Okay, understood? Now let us consider an example. F of x is equal to minus x square. First of all, we can find f dash of x, which is equal to minus 2x. Then we can find critical point. For that, we can equate f dash of x to 0. So f dash of x equal to 0 implies minus 2x is equal to 0, which implies x equal to 0. So here the number 0 is called the critical point C. Okay. Now we can draw number line. Here the point is 0, then plus infinity, here minus infinity. And we can take one number which is sufficiently close to and to the left of 0. Okay, here the value of C is 0. So we can take one number which is very close to the number 0 and to the left of 0. Okay, let us take the value of x as what? Minus 0.5. So if x is minus 0.5, then what is the sign of f dash of x? F dash of x is, here it is minus 2x minus 2 into minus 0.5. Okay, minus 2 into minus 0.5. That means minus into minus is plus, 2 into 0.5, that is 1, which is greater than 0, positive. Okay, so here the sign is positive. And we can take one point which is sufficiently close to and to the right of C. Right of C means here to the right of 0. So we have to consider an example in such a way that it is very close to the number 0 and which is more than the number 0. Okay, on the right part of 0. So we can take the number plus 0.5. Okay, then f dash of x is equal to, here minus 2 into 0.5, which is equal to what? Minus 1, which is less than 0, that means negative. Okay, so here negative. So the change is from positive to negative as x increases through C. Okay, so here the sign of f dash of x changes from positive to negative as x increases through C. That means f dash of x is greater than 0 at every point sufficiently close to and to the left of 0. Okay, in the left of 0. And f dash of x is less than 0, negative. Okay, less than 0 at every point sufficiently close to and to the right of 0. The change is from positive to negative. So we can conclude C is a point of local maxima. Here C means 0. Okay, so we can say x equal to 0 is a point of local maxima, and the local maximum value is given by, local maximum value is equal to f of C, here f of 0, which is equal to f of x is minus x square, so minus 0 square, which is equal to what? 0. The local minimum value of the function is what? 0. Clear? Now let us take another example. F of x is equal to x square. Here also we can find f dash of x 2x. Then f dash of x equal to 0 implies 2x equal to 0, which implies x equal to 0. So we got the critical point C as 0. Now we can check the sign conversion. Here the number 0, infinity, minus infinity. Okay, you can take a point sufficiently close to and to the left of 0, like in the first example. Okay, so here I take the x value as minus 0.3. Okay, and f dash of x is equal to what? 2 into minus 0.3, which is equal to minus 0.6, less than 0, negative. So here the sign is minus, negative. And we can take a point which is sufficiently close to and to the right of 0. So we can take one point x equal to some 0.4. Okay, a positive quantity which is very close to 0. Okay, and f dash of x is equal to 2 into 0.4, which is equal to 0.8, and it is greater than 0, that means positive. So minus, here it is plus. So the sign changes from negative to positive. Okay, f dash of x changes sign from negative to positive as x increases through c. Okay, that is f dash of x is less than 0 at every point sufficiently close to and to the left of c, and f dash of x is greater than 0 for every point sufficiently close to and to the right of c. So we can conclude c is a point of local minima. Clear? So here we can write x equal to 0 is a point of local minima, and the local minimum value is given by replacing x by 0 in f of x, that is f of c. Here f of 0, 0 square, which will be equal to 0. So here the local minimum value is equal to 0. Clear? Now we can consider one more example. F of x is equal to x cube. F of x equal to x cube. Here f dash of x is equal to 3x square, and f dash of x equal to 0 implies 3x square is equal to 0, x square equal to 0, x equal to 0. Okay, critical point is 0, 0, infinity, minus infinity. Okay, here also we can take one point which is sufficiently close to and to the left of 0. So x is equal to, let it be minus 0.1. Okay, you can take any number which is very close to and to the left of 0. Okay, and we can check the sign of f dash of x. F dash of x is equal to 3 into 3x square. So 3 into minus 0.1 the whole square. So 3 into 0.1 square, minus square is plus, and 0.1 square is 0.01. Okay, which is equal to 0.03 greater than 0, positive. So here the sign is positive. And we can take one more point which is very close to, sufficiently close to and to the right of c, right of 0. So we can take one number x is equal to 0.3. Okay, so here we can write f dash of x is equal to 3 into 0.3 the whole square, which is equal to 3 into 0.09, which is equal to 0.27. This is also greater than 0, positive. Okay, since it is a square, if you put any number instead of x, whether it is positive or negative, the answer or the value of f dash of x is always positive. Okay, so here also positive. So it means that f dash of x does not change its sign as x increases through c. Clear? F dash of x does not change its sign as x increases through c. So here x equal to 0 is neither a point of local maxima nor a point of local minima. And in fact, we can conclude x equal to 0 is a point of inflection. Clear? So here we can write x equal to 0 is neither a point of local maxima nor a point of local minima. And hence x equal to 0 is a point of inflection. Okay, these are the three different situations in first derivative test. Clear? Now we shall discuss the second derivative test. Let f be a function defined on an interval I and let c belongs to I. Let f be twice differentiable. Twice differentiable means the second order derivative of f exists at x equal to c. Okay. Then x equal to c is a point of local maxima if f dash of c equal to 0 and f double dash of c is less than 0. If these two conditions are fulfilled, then we can say c is a point of local maxima. And the value f of c is called local maximum value of f. Okay. And the second one is x equal to c is a point of local minima if f dash of c equal to 0 and f double dash of c is greater than 0. F dash of c equal to 0 and f double dash of c greater than 0. So these two conditions are satisfied, then we can say c is a point of local minima. Clear? And in this case, f of c is local minimum value of f. Clear? And the test fails if f dash of c is equal to 0 and f double dash of c is equal to 0. If f dash of c and f double dash of c are both 0, then the test fails. That means the second derivative test fails, and in this case we go back to the first derivative test and we have to check whether c is a point of local maxima or local minima, or c is a point of inflection. Okay. So I repeat, second derivative test. Let f be a function defined on an interval I and let c belongs to I. Let f be twice differentiable at c, that means the second order derivative exists at x equal to c. Then x equal to c is a point of local maxima if f dash of c equal to 0 and f double dash of c is less than 0. That means the value of the second order derivative is negative or less than 0 at the point c. Then the value f of c is called the local maximum value of f. Okay. And x equal to c is a point of local minima if f dash of c equal to 0 and f double dash of c is greater than 0. That means at the point c, the second order derivative is greater than 0 or positive. Okay. So in this case, f of c is local minimum value of f. And the test fails if f dash of c equal to 0 and the double dash and f double dash of c is also equal to 0. So in this case, we go back to the first derivative test and we have to check whether c is a point of local maxima or local minima or point of inflection. Okay. The second derivative test is often easier to apply than the first derivative test. Okay. So in most of the problems we check using the second derivative test, and if the test fails, then only we go back to the first derivative test. Okay. Let us consider an example. F of x is equal to some x square plus 3. First of all, we can find f dash of x. It is 2x, and f double dash of x 2. Okay. So the first order derivative and the second order derivative exist. Now we can find the critical point. F dash of x equal to 0 implies 2x is equal to 0 or x equal to 0. Then the next step is we have to put x equal to 0 in f double dash of x. So at x equal to 0, f double dash of x is, that is f double dash of 0 equal to what? Here it is a constant, so 2. That means it is greater than 0. So at x equal to c, f double dash of c is greater than 0, positive. So by second derivative test, what we can conclude? If f dash of c equal to 0 and f double dash of c is greater than 0, then f has a local minimum value. Okay. So therefore f has a local minimum value at x equal to 0, and that value will be equal to local minimum value is equal to f of 0, f of c. Okay, so here 0 square plus 3 which is equal to 3. Clear? So if the second order derivative is greater than 0, that means positive, then the function f has a local minimum, and f double dash of c is less than 0, negative, then the function will have a maximum value, local maximum value. Okay. Now the next thing is maximum and minimum values of a function in a closed interval. Okay. Let us consider a function f given by f of x equal to x plus 2. Comma x belongs to 0 comma 1. That means the function is defined in an open interval 0 1. So here we can draw a rough sketch of the function. Your x value, corresponding y value is x plus 2. So if it is minus 2 plus 2 is 0, minus 1, then plus 1, 0, 2, then 1, 3, and when x equal to 2, y equal to 4. X-axis and y-axis, then 1, 2, 3, 4, 5, and so on. Minus 1, minus 2, minus 3, minus 4, minus 5, etc. 1, 2, 3, 4, 5, etc. Here minus 1, minus 2, minus 3, minus 5, etc. Okay. Minus 2, 0. Here minus 1, 1. Here we can mark the point. 0, 2. Then 1, 3. 2, 4. Okay, and so on. We get a linear graph. Okay, this is y is equal to x plus 2. Now let us consider the function in the given domain. X belongs to 0, 1. That means this much portion only. So the graph reduces to this much only. Okay, this line portion. So clearly we can say the function f of x is continuous in the domain open interval 0, 1. Here there is no break in this portion. So we can say the function is continuous in 0, open interval 0, 1. Here we can write 0 less than x less than 1. We can add 2 on the inequality. 0 plus 2 less than x plus 2 less than 1 plus 2. So 2 less than x plus 2, that means f of x which is less than 3. Okay, that means the value of f of x lies between 2 and 3 in the given domain. So it will be more than 2 and less than 3. But we cannot say the least value and the highest value. That means the minimum value and the maximum value. If there is an equality sign, then we can say 2 is the minimum value and 3 is the maximum value. So here it is not like that. It is in open interval 0, 1. So we cannot write that. 2 less than f of x less than 3. That means there is no minimum value and no maximum value. And one more thing you have to notice that the function do not have a local maximum or local minimum value in this particular interval. Okay, so here there is no local minimum value or the local maximum value. So here I am going to extend this domain. I am going to write x belongs to some closed interval 0, 1. Okay, closed interval 0, 1. Now also the function do not have a local maximum or a local minimum value, but we can find a minimum and maximum value in this case. Look at that. This can be written as 0 less than or equal to x less than or is equal to 1. We can add 2. 0 plus 2 less than or equal to x plus 2 less than or equal to 1 plus 2. That is 2 less than or equal to f of x less than or is equal to 3. That means the minimum value is 2 and the maximum value is equal to 3. Okay, so this is called the absolute maximum and the absolute minimum. Here the minimum value is 2 and this value is called the absolute minimum or the global minimum, or we can say the least value. Okay, and the number 3 is called the absolute maximum value or the global maximum value or the greatest value. Clear? So the maximum and minimum values in a closed interval are respectively called the absolute maximum and the absolute minimum. Okay. Now consider the graph given below. Here the function f is continuous. It is a continuous function defined on closed interval a d. Okay, the function f is defined on closed interval a comma d, and we can observe that at the point b the function attains its local minimum value. Here this point. Okay, so at point b the function attains its local minimum value, and the local minimum value is given by f of b. Okay, and here at the point c the function attains its local maximum value. Here it is the local maximum value, and the local maximum value is given by what? F of c. So we can conclude at x equal to b the function attains its local minimum and the local minimum value is f of b. And at x equal to c the function attains its local maximum and the local maximum value is f of c. And what about at the points a and d? So it is evident that at the point a the function attains its maximum value. From the graph it is clear that at the point a the function attains its height, maximum value. So this is known as absolute maximum value. Okay, so it is an absolute maximum value, and here local maximum, here it is local minimum, and at the point d the function attains its least value. Okay, minimum value. So this is called absolute minimum. Clear? So f has an absolute maximum value at x equal to a, and absolute maximum value is given by f of a. Okay, and f has an absolute minimum value at the point d, and the absolute minimum value is given by f of d. Clear? Further, note that absolute maximum value and the absolute minimum value is different from local maximum value and local minimum value. Okay, the absolute maximum and absolute minimum is different from local maximum and local minimum. Clear? Now we move on to the next theorem. Let f be a continuous function on an interval I is equal to closed interval ab. F is a function which is continuous and it is defined on an interval, closed interval ab. I is equal to closed interval ab. Then f has the absolute maximum value and f attains it at least once in I. So here f has, the function has absolute maximum value and f attains it at least once. That means f has minimum one least value. Okay. Also f has the absolute minimum value and attains it at least once in I. In the particular interval I, f attains its absolute maximum and absolute minimum at least once. Okay. I repeat, let f be a continuous function on an interval I is equal to closed interval ab. Then f has the absolute maximum value and f attains it at least once in I. Also f has the absolute minimum value and attains it at least once in I. Now the next theorem is, let f be a differentiable function on a closed interval I and let C be any interior point of I. F be a differentiable function on a closed interval I and let C be an interior point of I. Then f dash of C equal to 0 if f attains its absolute maximum value at the point C. Okay, if f attains its absolute maximum value at x equal to C, then what happens? F dash of C will be equal to 0. Clear? Similarly, f dash of C equal to 0 if f attains its absolute minimum value at C. So, generally we can say f attains its absolute maximum or absolute minimum value only when f dash of C is equal to 0. Clear? Now we have a working rule to find the absolute maximum or the absolute minimum value. So here there are 4 different steps. Step 1 is find all critical points of f in the interval. Okay, we have to find the critical points first. So that we have to equate f dash of x to 0. Okay, first order derivative to 0. That is, find points x where either f dash of x equal to 0 or f is not differentiable. Okay, that points we have to find it out. Critical points. After that, take the n points of the interval. So in the given interval, closed interval, we have 2 n points. That points we have to take. Step 3, at all these points means listed in step 1 and 2. That means critical points including the n points. We have to take the critical points and instead of that we have to take the n points of the interval. Okay. Calculate the value of f. In these all points we have to find the value of x. Fourth step is identify the maximum and minimum values of f out of the values calculated in step 3. So in step 3 we get some values of f. So we have to check which one is greater or which one is smaller. Okay. So this maximum value will be the absolute maximum and the minimum value will be the absolute minimum. Okay. The greatest value among them will be the absolute maximum value and the least value among them will be the absolute minimum value. Clear? Now look at this example. Find the absolute maximum and minimum values of a function f given by f of x is equal to 2x cube minus 15x square plus 36x plus 1 on the interval closed interval 1 comma 5. We have to find the absolute maximum and the absolute minimum value. Okay. For that we can find f dash of x 6x square then minus 30x plus 36. We can take on 6 common, 6 into x square minus 5x plus 6. So we can factorize this one, x minus 2 into x minus 3. Okay, x square minus a plus b into x, here 2 plus 3, 5. Okay, so x square minus 5x plus ab, minus 2 into minus 3 is what? Plus 6. Clear? Now we can find the critical points. For that we can equate f dash of x to 0. F dash of x equal to 0 implies 6 into x minus 2 into x minus 3 equal to 0. Or x minus 2 equal to 0, x minus 3 equal to 0. X equal to 2 or x equal to 3. So these are the critical points, x equal to 2 and x equal to 3. Now we can take the points in the interval also 1 comma 5. Okay, so first of all we can find f of 1. So 2 into 1 cube minus 15 into 1 square plus 36 into 1 plus 1. 2 minus 15 plus 36 plus 1 which is equal to minus 13 plus 37 equal to 24. Okay. Now we can take the point 2, f of 2. So 2 into 2 cube minus 15 into 2 square plus 36 into 2 plus 1 which is equal to 2 into 8 minus 15 into 4, 36 into 2, 72 plus 1. 16 minus 60 plus 72 plus 173. So which is equal to minus 44 plus 73 which is equal to 29. Now we can find f of 3. F of 3 is equal to 2 into 3 cube minus 15 into 3 square then plus 36 into 3 plus 1. So it is equal to 2 into 3 cube is 27, then minus 15 into 3 square is 9, 36 into 3, 108, then plus 1. So it is equal to 54 minus 135 plus 109, and that will be equal to 28. Okay. Now one more point is the number 5. So f of 5 is equal to 2 into 5 cube minus 15 into 5 square plus 36 into 5 plus 1. So 2 into 125 minus 15 into 25 then plus 36 into 5 180 plus 1 which is equal to 250 minus 375 plus 181. So 250 minus 375 it is minus 125 then plus 181 which is equal to 56. Okay. Now we have to compare all these values. So here 56 is the largest value, greatest value. Okay. So we can conclude the absolute maximum value is equal to 56. So the absolute maximum value is equal to 56 at x equal to 5. And what is the minimum value? Here the least value is 24 at x equal to 1. So the absolute minimum value equal to 24 at x equal to 1. Okay, so in such a manner you can solve each and every problems. Okay, so that's all for today. I think you understood the concept. If you have any doubt, you can ask me in the comment section. Thanks for watching. Thank you.